Okay, so by right, after using this module, after this discussion, you should be able to explain all the instrumentations in terms of principle and methods analysis for AAS. Okay, appropriate techniques for analysis of different sample. Display competency to interpret data. I think it should be no difficulty because the data is generated from the machine. Spectrum disturbances usually also being counted by the machine itself. Okay, so just a quick recap. This is what we have discussed last week. The most important is for you to understand the principle of energy being absorbed by the electron in the atom, metal atom. Okay, so the absorption of the energy, which is in the form of photon. So there is an excitation. You can see the red dots representing the electron. The excitation of the electron. Okay, and then the relaxation of electron results in emitting energy, which should be equivalent to the energy given to the electron at the beginning. Okay, so the concept of here, nothing happens due to mismatch of wavelength. Okay, this one I'm not so sure whether I should explain to you, but in terms of if we are to excite the electron, okay, to a certain uh, uh, energy level, okay, the photon here, okay, has to be with sufficient energy or specific energy. So, for example, if the electron requires, let's say, 30 kilojoule for it to jump here to be excited to the high level, like these red dots. Okay, if you provide 25 kilojoule, nothing will happen. It will not like jump halfway or 1/4. No. Okay, the electron in the metal will stay at the ground level. Okay, so this is what the statement meant, that nothing happens due to mismatch of wavelength. So energy provided must be sufficient, must be correct in order for the electron to be excited. So that's why, if you remember, we're talking about a cathode lamp, hollow cathode lamp last week. Okay, and that hollow cathode lamp must be specific to the element, remember? So that's what, if you use the wrong cathode lamp and then you try to do it for different element that's not supposed to be, then it will not happen. You cannot get the reading. So the specificity of the photon provided by the hollow cathode lamp is very important to be correct. Okay. So this is what we have discussed. And the most important in the whole machines, the whole AAS machine, is the conversion of into free atoms, because it's atomic absorption spectroscopy. So we need this is the most important part that needs to be achieved, which is atom and the excited atom. Okay, so this is generally what you have at the beginning. So the solution, so it requires some vaporization into gaseous form and atomization. So the atomization requires flame. So one of the important part in atomic absorptions spectrophotometry is the flame atomizer. I think we did some discussion on the flame. So as you know, common users of AAS, which is suitable for you, for example here, food beverages, okay, because if you're looking for metal content in the food, so it's suitable for your application. All right. All right. This one, I think we have discussed a lot, yeah, during last week. But just to give you the idea, for example, this is the dedicated hollow cathode lamp for sodium. Okay, so it can be used to analyze sodium in the sample, and you can see it only give out specific wavelength. Okay, so only sodium atom will absorb this, and it will be the transmission, yeah, the transmitted. I will explain what is transmittance after this. Will be detected by the detector. So if you like the element does not contain sodium, then it will not absorb 589 nanometer. Okay, so that's why if you like have other element, plumber maybe or potassium, then you cannot get the reading because it will only absorb specific wavelength of the energy provided. Okay, so this is how the detection happen. Okay, sodium will absorb this energy, this specific energy. Okay, the higher the concentration of the sodium, the higher the absorbance will be. Okay, so what will be detected uh, by the detector is what is left, the transmittance, the transmitted energy that is left after the absorbance by the sodium content in that sample. So if you look at the equation, so transmittance, okay, that is recorded by the recorder will be equivalent to, this is what we call as Beer-Lambert's law, negative log, well, we look at the the calculation example. A stands for absorbance, okay. ABC is actually the absorptivity coefficient, which is A. B is the path length. Path length depends on the cuvette or the sample holder. So I'm not sure whether um, it is applicable for AAS. So this equation is not applicable for AAS. But if you use UV visible spectrophotometry, then this equation is relatable to the uh, machine. Yeah? So C is the analyte of the concentration. So, well, you will not be doing the calculation anyway. So let's look at a type of question. So let's say a sample has percent transmittance of 70%, meaning that the recorder records 70% of transmittance. So what is the absorbance? So a percent transmittance of 70% is the same as transmittance of 0.7. And by putting in the equation, we can calculate the absorbance of the sample. But again, you don't need this. You only need the final concentration, right? So the absorbance will be converted into concentration. So that's why from here, the absorbance is related to concentration. And these are all constants based on the machines. So this is just to show you what is the theory behind the detector. Okay, so configuration for absorption measurement. Okay, this is what we have discussed last week. Okay, this is basically the detail of hollow cathode lamp. So inside the hollow cathode lamp, there is inert gases that is heat up, and that inert gas is the one that will excite the metal of interest that you want to analyze. Okay. So remember about emission spectrum, atomic spectrum that I mentioned last week. So this is what we call as atomic emission spectrum. So what happened is inside the metal atom, this is metal atom. So this is excited metal atom. So the one that is excited are electrons, yeah? Electrons inside the metal atom. So once the relaxation happen, so electron will go down to lower energy. Okay, so it's not just one electron, it involves a few electrons. Okay, depends on the electron configuration of the metal. So it will result in a specific fingerprint, yeah, fingerprint of atomic emission spectrum unique to the metal. So this is what we're talking about. The hollow cathode lamp provide specific energy, and this will give out a specific atomic emission spectrum based on the configuration of electrons involved in the metal. And this is the one that being uh, absorbed. Okay, so again, this is just a background for you to know how the machine works. Yeah, right? How the hollow cathode lamp works. Okay, but very important, it is specific. It cannot be used for all. Okay, there are other source of energy. Yeah, we can use electrodeless discharge lamps, but this one usually quite rare. Usually we have hollow cathode lamp. Yeah, and we also have light chopper to clean up some lights. Okay, there are possibly emission from undesirable sources, organic matter in the sample, because we do not want that. We want the metal. We don't want any other organic material to interfere with the reading. So the machine will have light chopper to help reduce the unwanted emission. Okay. And of course, the atomizer, I think we have passed that. Monochromator also clean up. Okay, how the monochromator clean up? You can see this is where the spectrum of interest. Okay, this is the whole emission spectrum probably, and the monochromator help to clean up. Yeah? And then we focus on the spectrum of interest, the one that is of our interest. So instead of having a lot to analyze, it analyze one spectrum that is important. All right, so this is detector, and the most important, you did ask about whether we can, what kind of solvent, right? You need to use for the analysis. For AAS, it has to be in aqueous form. So if your sample is not in aqueous form, you have to do some extraction process. Extraction meaning that you extract from organic and then into aqueous. Okay, you have to do some all these sample preparation steps. Sometimes, if your sample is solid, you need to degrade and solubilize to release all metals for analysis. If your sample is already in liquid form, you probably need to filter to make it clean. If there is, for example, here, if you have organic, you need to extract the metals from the sample metric into solvent suited for the analytical method to be used. Okay, and you think that the concentration of metal inside the sample is too low, you need to pre-concentrate first, because if the machine does not have a very good limit of detection, you might not be getting reading. So you probably have to pre-concentrate by doing extraction also, right? And sometimes you have a group of metals in that samples. It is possible, if you are using AAS, you need to separate, or you just focus on single analyte. But we will discuss about AES, ICP AES, which is more robust, okay? And then you can use for multiple analytes. Okay, to dilute the matrix sufficiently, what is the meaning of matrix? Matrix is where the samples, where the metals are from. For example, if you're talking about coconut water, So inside the coconut water, there are sugar, for example, glucose, there are any other materials in the coconut water. So that is called matrix. Okay, meaning that it's not just potassium. You have to think about the matrix inside the whole coconut water. So to make sure that the matrix inside the coconut water uh, will not interfere with the reading of potassium. To separate different chemical forms of analyze. Okay, this one is also if you need to do this, but sometimes, most of the time, it's okay because you're working with liquid. Okay, right. So this is generally the flow chart of how you do, okay, for sample preparation. Okay, so if you have dry sample, okay, the best is to apply the one of the method is to dry etching, meaning that you put everything in an oven first, okay, to not to call denature, how to to dry all the organic content and water. Okay, so at least the organic content will be denatured. Okay, but the metal stays there, right? It is advised the temperature limit should not be beyond 500 because if that, then the metal might be oxidized. Okay, so we don't want the nature of the metal to be compromised. Okay, other than dry etching technique, you can use what we call as wet digestion technique. So wet digestion technique is by using highly concentrated acid. So the acid that you use should not create precipitate. Yeah, should when you mix it with the acid, it shouldn't create precipitate. That's the type of acid. Yeah, you have to make sure, right? And these are some of the acids, yeah, dilute acid for dry ash, for easily oxidized metals. But if you are working with alloy steel, then you have to use concentrated acids. Yeah? And then if you are working with silicates, rock samples, then you have to use what we call as HA, hydrofluoric acid. This one is very dangerous, yeah? Can dissolve your bone. Okay, so even the vapor can affect your bones, yeah? Can degrade your bones. So make sure if you have to use this, be careful. Yeah. Other than that, there is a mild technique, what we call a microwave assisted. Yeah. So is to use microwave assisted technique, but you need to have the setup. Yeah? It's not like the microwave that you use in the kitchen. They have a proper microwave setup. If you have this, then it is much easier for you to do sample preparation. Okay, so this is something that you need to do. All right. And next is to have a calibration curve by preparing by using standard solution. Okay, so this is one of the best, what we call a standard addition method. I think I have sent to you last week the link to my recorded video detail on the standard addition or without standard addition, and there is external standard. Okay, so in most cases, the presence of interference, or so-called matrix, yeah, imagine the coconut water, uh, is easy if you can counter this issue by using standard addition method. So what is standard addition method? Okay, imagine this. So imagine this is your coconut water. It's not supposed to be look like this, but I'm just showing that, okay, in the coconut water, there is what we call as matrix, like glucose or any other metals or any other compound that exists in the coconut water. And the blue round object is the one that you wish to detect, which is in this case, let's say potassium, the blue sphere. Okay, so this is what we call as matrix. And this is standard solution. Standard solution means that there is no matrix effect. Okay, so since you are doing the sample, right? You can do separation, but it's very difficult to separate and then do analysis. So instead of doing separation, we can do what we call a standard addition method. So this is how standard addition method, because you need to prepare calibration plot first before you can run the AAS, right? So let's say you are doing, let's change lead to potassium, okay? So this is the coconut water. The red represent the coconut water. Okay. So we put a fixed amount of coconut water, which contain the matrix. Okay. In, let's say you want to do 4 readings. Okay. All right. And then you can see all the volumetric flask contains a similar amount of coconut water. Okay. So by adding, if let's say you want to have 5 ppm of potassium, then the first volumetric flask should be added with 5 ppm. So the second should be added with 10 ppm of standard solution, standard solution of potassium. And the third volumetric flask with 15 ppm of standard solution. So you can extend, okay, depends on the range that you need to work with. So by doing this, we eliminate the issue of interference from the matrix just now. Okay, that's why it is called standard addition method. Is added with a matrix. Okay, so this is very important for you to know before you can do a calibration curve, because once you have that, let's skip the hydride generation. Okay, this is, we have done the interferences we have discussed last week, so I'm not going to discuss back. So this is from the reading from AAS, okay, thermoscientific. So you can see this is the results. Okay, so the first 3 solution is the standard that has been prepared, so that the calibration plot can be generated. So if you prepare a wrong standard, then you get a wrong calibration. Okay, so this is the sample. This is the sample that you submit. And the concentration, you see the concentration is in ppm, milligram per liter, will be generated for you based on the calibration plot that is constructed by the standard solution. So that's why the preparation of standard solution is very important. If you did wrongly, then this whole thing, this whole value also will be wrong. Okay. So as I said, you don't need to worry to do any calculation. Everything will be calculated for you. But in here, I think, I don't know whether they do replicates, but it should have replicates. For example, standard 1 should be 3, standard 2 should be 3 replicates. So everything should have standard deviation reading. Okay. Same goes to the sample. Each sample should have a minimum of 3 replicates. Yeah. So this is the example. Okay. Are you okay? Before we move on to emission. Right. Okay. So I think this is just a revision. Yeah. So for emission, as I mentioned previously, let's look at what's the difference. In terms of theory, where is it? Okay. So absorption and then emission. So now we are focusing on emission instead of absorption. So what's so special about emission? Okay, let's look at, okay, for this atomic emission. Again, you need to know the basic principle of instrumentation, which is quite similar to AAS. It's just that now we are focusing on emission. and all the sources, all the components, and you can see that explain the difference of AES and AES. So usually final exam question, we have this. You have final, yeah? Okay. All right, let's move on. Okay, so you can see there is similarity. Prepare sample, convert solution into aerosols, and then you have atomization, excitation, and then detection of emission lines. Yeah, so it's quite similar to AS. So AES is used for determination of elemental composition. Okay, the sample could be tested. The sample to be tested could come from any other number of sources. So I think it's quite also similar to AES. Okay, each sample to be tested must be prepared. All right, same. Okay. All right, again, it has to be nebulized, aerosolized, okay? Right, okay, let's move on. What's the difference is sample, right? Samples, again, is quite similar. Okay, you can see that I think is, all right. You can use also flame for emission spectrum, and we can also use plasma. So I think I did discuss a bit on plasma. So plasma is heat actually, and the heat is generated by using argon plasma sometimes. Okay, so this is the structure. Where is it? So this more or less is similar to AS. So I don't want to repeat that. So the most important is the plasma. Okay, so plasma, where is it? Where's it? Okay, this is how it looks. Okay, so this is the argon gas flowing here, and we have radio frequency induction coil that ionize the argon. So when the argon is ionized, okay, you can see this will produce plasma. So plasma is actually heat, okay? And this process will generate a very high heat. It is not comparable to hollow cathode lamp, yeah? It is much higher. So you can see that it can go to 4,000 Kelvin, yeah, based on the table just now. Okay, so this is something special with using AES. Okay, this one, the atomization process is similar. It's just how the plasma, right? So the application, okay, for AS, it's just one view absorption, and then of the wavelength, and then transmission is recorded, and then when with the calculation you can calculate absorption. But for plasma, okay, the detection is a bit different because it is based on emission. So emission from plasma, okay, it can be viewed by radical view and axial view. So by using these two types of viewing of the emission, low detection limits can be achieved. Okay, so this is actually the difference between normal AAS and then the ICP AAS. Yeah? The detection of the recording of the emission, they have two types of view. Okay, and you can see this axial view will help to have better detection limit. Yeah, that's why this machine is much expensive, much more expensive, and it helps you to detect with lower concentration. So this is what it means is meant by a radical view and the axial view. So I actually don't know how they view, because usually it's the engineer who understand the machine. Okay. Uh, there is detail of how the theories of how to read the axial and the radical view. All right. This is what we call as spectral interference. We did discuss about spectral interference and chemical interference last week. Okay, so this is something usually already been solved by the supplier of the machines. So we don't need to really worry about that. Okay, so you can see like this is the interference effects of plutonium on calcium. So there are, of course, we can imagine that the emission spectrum of different element might be overlapping. Okay, so this is example. Okay, the spectrum for plutonium and spectrum for calcium. So if we are analyzing calcium, there is interference from plutonium, for example. And this is also another example. If we are to analyze aluminium, there is also probably plutonium interfering with the spectrum. Okay, since the detection is all based on emission spectrum, so this is an issue. But you can see that it is 1000 compared to 10 ppm. So meaning that the existence of plutonium has to be very high in the sample in order to interfere. And they usually have the manufacturer's software will automatically perform correction. So no need to worry. But this is something possible that can happen. All right. Matrix interference, okay, and method of compensation. We have learned just now standard addition, so we don't need to worry about matrix. If you use standard addition to construct the calibration plot, then it should be okay. Yeah, right. Okay. So you can see this is what when we have matrix. But let's imagine the coconut water just now. And then this is the analyte. So this is the measured spectrum. So when we have this kind of spectrum, the machines will have some issues because when the machines analyze, they require a clean spectrum. Okay. But this one, okay. So we can think about dilution, matrix matching, use of internal standards. Okay. So you do need to read internal standard, external standards. Okay. But this one, you can only observe. Probably you read first or you run the sample first. And if you think that there is something wrong with the reading, then we need to do some dilution. Okay. The first thing that you can do is try to dilute first. Okay. If the dilution helps, then it should be okay. Right. Standard addition, okay, the one that we discussed. Okay. So detection limits, AAS detection limits are generally better in all cases. But of course, AES, ICP, AES is much better. Non-metals and the halogens can only be determined by ICP. So AAS cannot do non-metals, okay? Even the non-metals and halogens, only selected non-metals and halogens only. It's not all, yeah? So you have to check with the manufacturer of the machines. Optimum detection can only be achieved when vacuum monochromator is used. So that one, you have to check with the manufacturer. For mercury and those elements that form hydrides, okay, mercury is specific. You have to use cold vapor, mercury or hydride generation. So that's why if you want to run mercury, you should go for mercury analyzer. Yeah, because they have very specific cold vapor mercury. So most of the AAS does not suit mercury. You have to go specific for mercury analyzer. All right, spectroscopy. Okay, this one is done. All right, so application, you can see here. So ICP MS is mass spec. So I don't discuss mass spec here. Mass spectrophotometry is not under this. So only absorption AA, which is atomic spectroscopy, and emission spectroscopy. O stands for optical. So it's just the matter of the machines is using optical technique for the reading. So you can see environmental should be water. AA, soil is difficult, so ES. So this is pharmaceutical, right? In your case, you want to do analysis of potassium, so AS is okay. All right. All right. So that's it for my part. So I just want to discuss a bit. This is an assignment for you. The main lecturer for this is Dr. Bimo. So I will ask Dr. Bimo how many percent of assignment mark from me. But this is my assignment. A simple tutorial that you have to answer. Okay, so here the question is, copper and zinc are isolated from tissue samples by digesting with nitric acid after first removing fatty tissue. Okay, so the concentration of copper and zinc in the supernatant are determined by AAS using flame, yeah, acetylene flame. Tissue samples are obtained. Okay, this is the story, blah, blah, blah. Describe appropriate metrics for external standards and for the blank. So you have to read about external standards, tell about the metrics, how they prepare the metrics. Why is the background correction necessary for analysis of zinc, but not for analysis of copper? A copper hollow cathode lamp has several emission lines. Explain why this method uses the line at 3 to 4.8 nanometer. So you have to answer all this. And you are given the reading. To evaluate the method described in above, a series of external standard is prepared and analyzed, providing the result shown here, which is, okay, where is the result? There, okay, so why is not moving? Just a moment, yeah. Where is the next question? A bovine liver standard reference material was used to evaluate the method's accuracy. After drying extracted sample, FDT issued sample gives an absorbance of 0.023. Okay, report the amount of copper in the sample as microgram copper per gram FFDT. So describe possible protocol in analyzing mercury sample in oil and gas sample. Discuss advantages of flame atomizer. Okay. Okay, so I think this is something for you to take some time to read first. And then if there is question on this tutorial question, you can just ask me. Don't hesitate. Okay, you can ask me. But this one something that you have to complete to get the marks for assignment marks. Yeah. It's up to you how long you need. But of course, don't take too long. Okay, because Dr. Bimo will be continuing this lecture. And of course, there are some other assignments from him. He's the main lecturer for this subject. I'm taking one credit and the rest are taken by Dr. Bimo. Okay, all right. So Zubair? I think that's all from me. Any question?
Okay, Prof. Thank you. Thank you so much.
Mm.